Okay, hi there everyone. This is Dr. Schultz, and here I am. Say hello to you. In our lesson today, I'm going to address learning target number 3, which says I can solve problems which involve the motion of one object relative to another for cases in which objects share a common frame of reference. We're not going to do the latter part of that learning target, but we're going to focus on the first part of that. And what's a little bit different about this particular learning target is that now we're going to actually look at cases where you have two objects that are moving at the same time, and you want to get some information about how they are moving relative to each other. And that's different than what we've been doing up until now. Up until now, we've really just focused on one object at a time. So I'll just share with you kind of a strategy for doing this and for figuring out those problems. Probably your common sense is also going to be useful to you here because you might even be able to get some answers simply by thinking through the logic of the problems. Okay, so I'm going to present a word problem here. I would encourage you to pause the video right now and to read the problem to yourself. Oops. Sorry about that. Okay, now I'm going to read it again. The problem states that there are two cars moving in the same direction along a road. At a particular instant of time, car A is located 2 meters to the right of the starting line and is traveling at 20 meters per second. At the same instant, car B is located 8 meters ahead of car A, and it is moving at a slower speed of 15 meters per second. What is the relative velocity of one car with respect to the other? When will A pass B? And where will A pass B? So I hope that the setup here, before we get into any math or numbers, I hope you see what's happening. You know, you've got a slow car out in front, and you've got a faster car behind it that's going to catch up. And what's tricky about this is that you've got two things to deal with, and you want to figure out when do these two objects have the same position. You know, when does that happen, and where does it happen? So why don't we set this up? We're going to start off just with the number line because that kind of makes sense here. And my origin of my number line is going to be there. And I'm going to take the information from the problem. Car A is located 2 meters to the right of the origin. And car B is 8 meters ahead of car A, which means it must be located in a position of plus 10 meters. Okay, so that's the positions of those two objects. Now, let's put vectors on here to represent the velocities of these two objects. A is moving faster. So I'm going to represent its velocity with an arrow and label that 20 meters per second. And when I draw the velocity vector for B, I'm going to make it, you know, clearly smaller. And that's 15 meters per second there. I'm putting the pluses on there just to be like crystal clear about the fact that we're moving to the right. So you know, that's kind of worth noting here. Okay, now before we do anything else, I want you to think about what your intuition would tell you here. Intuition should tell you that A is going to catch up to B, okay? But your intuition might actually tell you something more about how fast A is approaching B. So if you were B and you were looking out of your rearview mirror, you're going to see A getting closer and closer. Ask yourself the question, how fast is A coming up to you? Forget about the surrounding landscape. Just focus on the fact that A is getting closer to you. I think intuition should guide you to the idea that A is getting closer to you not at 20 meters per second, but at the difference of those two speeds. So intuition would say that A is approaching at about 5 meters per second. Okay, and that's actually part of the answer to this, is that A is approaching at that speed. But let's set this up in a more formal way, and we'll see what other information we can get. Because you might be able to guess that 5 meters per second is the relative velocity, but what you probably cannot guess is where these two objects are actually going to meet up. Okay, so where on the number line is it going to be? And it's probably going to be past plus 10, but you have to do some math to figure that out. So what we do to carry this out is we have to establish a common frame of reference. Okay, so we're going to use the Earth as the common frame of reference, so FOR. And that's basically what our number line, that's what the origin indicates. So that origin is fixed in the Earth. Okay. So what I'm then going to do is I'm going to write an expression for the position of car A as a function of time in that coordinate system. So I'm going to write that as XAE, okay, two subscripts. And what that means is it's the position of object A with respect to the Earth coordinate system. Okay. Now, so that's the meaning of our subscripts here. We're going to be using double subscripts to show this, to show that one thing is relative to something else. This is constant velocity motion. I think we're supposed to assume this. And so if you were to just focus in on car A, and I said, where is car A? I hope you would start off by writing down the fact that it starts at plus 2 meters. And it's also moving to the right at 20 meters per second. So we're going to have to add on velocity times time. Okay. And so that gives us kind of a function here. If you wanted to, you could simplify it. You could say that this is going to be 2 plus 20t. So that gives you the position of A on the number line at any time that you would like. Okay. Let's do the exact same thing for B. So for B, we're going to have its initial position of plus 10 meters. And then we're going to add to that the displacement that happens with time, which in this case is 15 meters per second times t. Of course, that gives us 10 plus 15t. Okay. So these are the two functions that tell us where these objects are located on the number line at any time. What we want to do next is actually find out when the objects will actually occupy the same position. Now, since we've expressed both positions in the same frame of reference, the easiest way to do that is simply to figure out when is it true that the position of A with respect to the Earth is equal to the position of B with respect to the Earth. That's probably the easiest way to do it. And so let's solve that. So that would be 2 plus 20t is equal to 10 plus 15t. And let's do a little bit of math on this. I'm going to take 2 away from both sides. I'll take 15t away. And I can solve for t. And so that's a time of 8/5 or 1.6 seconds. That is when the objects actually will meet up with each other. Okay. So we've answered a question here about when the objects are going to pass. Now, how about where will they pass? So we know when. This is the when part. How about the where part? Sorry. And then I hope you know what to do next here. What we can do is take 1.6 seconds and we can plug it into either one of those functions. Let me pick what I think is an easier one. Let's do a with respect to the Earth. That's equal to 2 plus 20 times 1.6. On your calculator, 20 times 1.6 is equal to 32. 32 plus 2 is 34 meters. So these two cars meet pretty far down the line. They're certainly off the scale of our paper. You could go back. You could also show yourself that if you plug in the same 1.6 seconds for car B, you get the exact same answer of 34 meters. Okay, so that's the idea. Underneath here, we could think about this graphically. I'm going to just do a little graph here. And what I want to do is I'm going to jot my functions down here. I've got a with respect to the Earth is 2 plus 20t. B with respect to the Earth is 10 plus 15t. Okay. Now I'm going to show you graphically. This is kind of interesting. Let's graph these positions on a position time graph. For my scale on time, I'm going to start at 0 seconds. I'm going to go to 2 seconds. So that puts 1 right in the middle. 1.6 is going to be 1, 2, 3, 4, 5, 6 right here. I'm going to sketch a kind of a dashed line here. Okay. And then I want to represent position on the other axis. Of course, that's in meters. Time was in seconds. And my position, I suppose we could start it at 0. And we want to go up to some nice scale here. Probably the nicest thing to do is to just go up to 50 meters. And that means that every 4 blocks, it's going to be 10, 20, 30, 40. Okay. So this is, that's a reasonable scale. So the deal would be that we know that at 1.6 seconds that the cars have the same position. Their position would be at 34 meters, which would be right here. We also know that at a time of 0, that car B is at 10 meters. I'll represent that with a circle. And car A is at 2 meters, which is about there. I'm going to represent that with a square. Okay. So at 1.6 seconds, let me put both the circle and the square together because they're overlapping, right? And the idea is that if you look at these functions, these are basically formulas for lines. And, I hope you can see that if you plot out the position of car A squares, it's going to go like that. And if you plot out the position for car B, those are your circles, it's going to do that. And so that's what the overlap is. So again, the circle is B, the square is A. And clearly, after 1.6 seconds, they kind of change places, and A ends up ahead of B. And the nice thing about graphing this is you can kind of see visually that these positions change, they overlap, and then they kind of swap places. Okay. I'm going to show you one other thing you can do with this data, and that is, what if you wanted to find the relative position of B with respect to A. Okay, so we know that they happen to be at the same place at 1.6 seconds, but we don't really have a function for knowing like how far apart they are at any other time. So it's easy to get that, and you can basically say, well, the position of B with respect to A, so subscript B with respect to A, you can get that by subtracting, and you would take, for example, the position of B with respect to the Earth minus the position of A with respect to the Earth. This is kind of like a chain rule. Okay, and it's similar to the way we've defined the delta before, but B with respect to A, you have to do B with respect to the Earth minus A with respect to the Earth. So let's write that out. B with respect to the Earth is 10 plus 15t minus A with respect to the Earth is going to be 2 plus 20t. Let's carry out the math. 10 minus 2 is 8. 15 minus 20 is minus 5t. And what that tells us is that at a time of 0, for t is equal to 0, the position of B with respect to A is actually 8 minus 5 times 0, or plus 8 meters. Okay, that makes sense, because remember, at the beginning of the day, if you look at your diagram, B is 8 meters ahead of A. So that plus 8 meters totally makes sense on that. Okay. As time gets larger, that plus 8 meters is going to get closer and closer to 0, and eventually that plus 8 meters will become negative after 1.6 seconds, and that means that object B is now behind object A. Okay, so the plus and the minus is important here. B with respect to A gives you that. If you were to reverse this, try it. If you were to do the position of A with respect to B, okay, what you would get would basically be the negative of this. So it would be negative 8 plus 5t. And so at a time equal to 0, the position of A with respect to B is negative 8 meters. And that makes sense because at the beginning, A is behind or to the left of B by 8 meters. So that's where the negative comes from, because it's to the left. And as time goes on, that this negative 8 comes closer to 0 and eventually becomes positive, because A will then be ahead of B after 1.6 seconds. Okay, so the problem here that we've solved is you know, to look at relative positions. When do things meet? Where do they meet? We said that the relative velocity between the two of these things is that A approaches B at 5 meters per second. I didn't totally show you math on that, but let me just point out that if you look at the two functions that we have here, 2 plus 20t and 10 plus 15t, taking the derivative of those functions, right, whether or not you should get the rough idea here is that this is the velocity here. That's the velocity of A with respect to the Earth. This term out in front of the t, that's the velocity of B with respect to the Earth. And if you subtract those two things, you're going to get the relative velocity between the objects. So similarly to how we said this before, you could say that the velocity of B with respect to A is going to be the velocity of B with respect to the Earth minus the velocity of A with respect to the Earth. That's going to be 15 minus 20 is equal to negative 5 meters per second. The interpretation of that, the interpretation of that negative is that from A's point of view, from A's point of view, B is moving to the left. Okay? I'll say that again. Why do we have a negative sign here? When we use this chain rule for velocities, why do we get a -5? That means if you imagine that you are A in the faster car, from your point of view, B is actually moving to the left in your frame of reference because it's actually moving towards you. And as time continues, B will continue to move to the left, except now it is behind you. All right? So this chain rule is actually quite useful. You can use it for positions and for velocities. I know we haven't talked about derivatives yet, but you should know that the chain rule can directly be applied to the velocities of the objects as well. Okay? So there's some practice problems for you to work on in your packets. Please graph them carefully and solve them algebraically so that you get comfortable with how to do this sort of thing. Okay? All right, so have lots of fun. Bye.